Today I'm trying to figure out how this project here, this Gen, say probabilistic programming language from MIT. I need some music. Let's see what we can do. Just make a DRM free music. Okay. For introduction, there's so another probabilistic programming language embedded in Julia. Implementation details of let's just hop right into the how does this work again? You press this and that puts you in rebel mode. What does that do? Nope. Gotta add it somehow. How do I do that? Alright, Julia add package. There we go. Give me, so what is the, wow, that's hopefully working. Automates the implementation details of probabilistic inference algorithms. Gives users building blocks for writing efficient probabilistic inference algorithms that are tailored to their models. So hopefully, so one of the difficult things about probabilistic modeling is the writing of inference algorithms, because it's almost entirely different skill set from what you need to have to be a good modeler in the first place. And so if they can provide abstractions that makes that a lot easier, that would be really beneficial. Performance trade-offs, hybrid inference algorithms. So neural network inference is fast but can be inaccurate. Requires expensive training. Model-based inference is more computationally expensive, but does not require retraining and become more accurate. So we can mix them together. All right. So basically, all the benefits seem to be about better inference. Let's see if I can't find a. Trying to find a tutorial. Here we go. Is this working yet? All right. Introduction to modeling. Black box joy. Oh, these are on. These aren't even done yet. Okay, it's introduction to modeling then. Supervised learning, hybrid approaches, amortized inference compilation. All right, let's just get to it. All right. Cool, let's Spread these out a little bit. All right. Using Gen. So I've heard some good things about Gen. Never tried it before. It's gonna be the first time. I saw a cool thing where you could mix it in with, wow, that's taking a while. I gotta pre-compile it, huh? You can mix it in with useful, simulation programs. So you can take in some package that allows you to simulate something in Julia and just kind of make it work with Gen. So that seems to be particularly useful. Probabilistic models are represented in Gen as generative functions. The simplest way to construct a generative function is by using the built-in modeling DSL. Generative functions written in the built-in modeling DSL are based on Julia function definition syntax, but are prefixed with the gen keyword. The function represents the data generating process we are modeling. Each random choice it makes can be thought of as a random variable in the model. The generative function below represents a probabilistic model of a linear relationship in the xy plane. Given a set of x coordinates, it randomly chooses a line in the plane and generates corresponding y coordinates so that each xy is near the line. We might think of this function as building a house, is modeling house prices as a function of square footage, or measured volume of a gas as a function of measured temperature. Sure. All right. So how's this still running, man? I don't know if this is kind of customary for. Do you have to do this just once? I hope. So let's just look at this while this is loading. So passing in some vector of floats, getting the length. We begin by sampling a slope and intercept for the line before we've seen the data. We don't know the values of these parameters, so we treat them as random choices. These distributions they are drawn from represent our prior beliefs about parameters. In this case, that neither the slope nor the intercept will be more than a couple points away from zero. All right, so we have some kind of execution trace. This is kind of a list that's tracking all the random choices. This slope is normal 0, 1. I guess it's the name of the object inside the trace. Intercept also normal 0, 1. For I in this, we have, so ix, we're going to create an I object, a y object. This is a tuple. The return value of the model is not particularly important. Here we simply return n. All right. It's still working. So I honestly can't tell if this is an issue, some kind of bug, or if it really takes this long to precompile Gen. So I'm not used to that. I mean, I haven't worked much with Julia. I've worked mostly with Python and R, but there you import it, you install a library, and then you import it, and or at least all the time, if you're, I guess install steps for those libraries can take a while. You have to compile C code. Pass in some x values. Given this vector, the generative function samples a random choice representing the slope of a line for a normal distribution, mean 0 and standard deviation 1. And a random choice representing the intercept of the line for normal distribution with mean 0 and standard deviation 2. All right. Each random choice is annotated with a unique address. So I guess that's this thing here. A random choice is assigned an address using the trace keyword. Addresses can be any Julia value in this program. There are two types of address used: Julia symbols and tuples of symbols and integers. Note that for the for loop, within a for loop, the same. I want to know what a Julia symbol is first. I forgot. Symbols in Julia are the same as in Lisp, Scheme, or Ruby. However, the answers to the it seems that the reason a symbol is different from a string is that strings are mutable, while symbols are immutable, and symbols are also interned. Strings do happen to be mutable in Ruby and Lisp, but they aren't in Julia. And the difference is actually red herring, the fact that symbols are interned, i.e. hashed by the language implementation for fast equality comparisons, is also irrelevant implementation detail. So what is a symbol really? The answer lies in something that Julia and Lisp have in common: the ability to represent the language's code as a data structure in the language itself. Some people call this homoiconicity, but others don't think that alone is sufficient to allow language to be homoiconic. But the terminology doesn't matter. The point is that when a language can represent its code, it needs a way to represent strings like assignments, function calls, and strings that can be written as literal values. It also needs a way to represent its own variables. All right, so let's see here. We got eval foo. Foo's undefined. Foo equals hello. Eval foo. Oh, I see. So like putting it as so it's like putting a little colon in front of it makes it behave a little bit like an expression. Right. Interesting. All right. That seems to have some expressive power that I'd be curious to see how Julia takes advantage of, particularly in this probabilistic programming setting. Are we done yet? Oh, we're done. Oh, great. I feel like this music is definitely going to throw a DRM flag. I'm going to skip this song. Like 100% sure this is DRM. This is not a DRM protected song. RJD2. Okay, so we got, if I just run the model afterwards, what happens? some. I'm gonna just explicitly search for DRM free music in Spotify. Well, here we go. DRM free stream playlist. I guarantee you, it's all like weird techno stuff. But let's. Oh God. Oh no. It's all chip music. And like terrible jazz. Alright. Transfer to do. Okay, so wait, why does it produce? Oh, just a number of things. Got it. Alright, so. Alright, so let's see here. Crucially, each random choice is annotated with a unique address. A random choice is assigned an address using the trace keyword. Addresses could be any value. In this program, there are two types of addresses, usually symbols and tuples of symbols and integers. Note that, okay, that's really useful because that means that if you're going through a for loop, then, well, like you're doing here, I suppose, then you don't have to like make up a new name, a new address name each time, or address symbol each time you're doing this, right? You can actually add a little index to it. I've wanted to do that so often. It's a nice little feature. Note that within the for loop, the same line of code is executed multiple times for each time. There we go. Yeah, that's what I said. All right, so it's getting a distinct address because you're adding the little I here. Although the random choices are not included in the return value, they are included in the execution trace of the generative function. We can run the generative function, obtain its trace using the simulate method from the gen API. Do you need that little thing at the little semicolon? All right. What do I put excess in the little, make it a tuple? Let's look at that trace. Gen.get args trace. I don't know what the break here. Line. All right, so what are those the arguments that I passed into it? The trace of a generative function contains information about the execution. So the execution means like you ran a stochastic program and it produced one, and every time you run it, it executes differently. Each different execution is called a trace. You run it once, you get one trace, and so this is what we get. So we get this trace object. False union, false trie, gen, so a whole bunch of stuff. I suppose that's useful to somebody who understands what we're looking at. I mean, we should have, so we have at least values. So for y1, it's one index, right? I don't even know order. y1, I guess we got y1. This tuple here, what could that be? normal, which should give us one value. That's too high to be from a normal 0, 1. Could be a log probability maybe. No, it would be negative, wouldn't it? Huh. Okay, let's actually see what came out of a trace then. So let's go to a new block here. Isn't that what we got before? The trace also contains the value of random choices stored in map from address to value called a choice map. Get choices. So some kind of so y7 maps to this, y9 maps to this, but it's giving me a bit too much information. We don't know what this nan is, what this true is. I assume that these must be the sampled values, but no, they're all close to 1 point because the variance is low, right? 0.1 variance. Huh. But that would depend on the x value. 5, 4. So for 1, we had a negative 5. Did we see what the x value was? Nope. It's probably here in this arguments thing. Huh. Okay. So we're getting these 1.0. That's negative. Slope. Yeah, they definitely didn't have anything called intercept here. Oh, no, yeah, I did. Did I have it? Do I have an intercept? Yes, I do. So where's the intercept value? Is there a pretty print? Intercept. All right, that works. All right, so more interesting to the end are the values of the random choices. We simulate, we get the args. All right, we can pull out the individual values from this map using the subscript index. All right, let's get the slope. Great. In order to visually understand the probabilistic behavior of a generative function, it's helpful to be able to visualize its traces. That'd be nice. Let's see what a trace looks like. No. Is that a thing? Did we define what figure was? I don't know, I gotta do using figure or something. Using figure. it's gonna work. Anyway, so I expect I get something like this. Don't know what this plot the data set with. Julia scatter. And that's not it. Oh, no, that works. So let's say using plots. Okay, gotta add that thing. I now know, well, hopefully this will work and I can learn how to plot stuff. Ooh. But what we really want to see is this fancy inference stuff, predicting new data. Posterior inference. I want to see it do all this stuff, but I really want to see it do something interesting. Well, let's see what it does for posterior inference. Goodness grief. All right, so it's going to take forever to load that. So we're going to predict some new data using a generate method. That's going to be fun. Let's see here. Choice map constraints. I mean, so far I'm liking the look of this language. We got a do inference function. Okay, it's very nice and clean. Very Yeah, I'm starting to feel why people like Julia. And I'm curious to see, how do they handle inference in this? Is it like Stan, where it's kind of baked in, or do you have to do you do interesting things with inference that doesn't require you to be a computational statistician? I'll draw all these pretty plots when the time comes. It's a random model that generates a sine wave of random phase, period, and amplitude. Generates y coordinates from the given x vector by adding noise to the value of the wave at each x coordinate. Use a gamma 5.1 prior for the period and a gamma 1.1 prior on the amplitude. So phase here, prior, amplitude, and then there's no what's also interesting here is that there's no explicit, wait, never mind. Okay, I was going to say that there might, was there an explicit likelihood function, or could you just write the data as a function of the parameters? Because that would be pretty badass. Where's the, so you actually have this is your likelihood function, a normal distribution, so. But you could make that we can probably make that pretty tight, that variance. So like this is something I've been interested in because, you know, in simulations, you don't necessarily have a likelihood function. You just kind of have some inputs and you deterministically generate some outputs, or stochastically generate some outputs, but those outputs may not have their own likelihood function. But this looks like it has the same requirement, kind of requirement for Bayesian stuff to work, but so what are we gonna do here? We gotta get a random phase, we sample a phase, sample a period, sample amplitude, create a point on the y-axis that is 2 pi times x divided by period plus phase. And then you only sample this once, right? Great. So and then we put a little bit of noise around that. Fantastic. What does this render do? We're done plotting. Great, let's do some plots. Using plots. So I gotta import like fear. Julia plots figure scatter import. How does that work? Using plots. Yeah, you just load it. So what is not working here? Oh, maybe this didn't work. Oh, I got some kind of error. Evaluation into close module breaks the incremental compilation because the side effects will not be permanent. Right. All right, I guess we have no plots then. So let's just try one more thing here. Restart and clear output. Let's try importing that first in case. Let's restart and clear outputs. That's odd, just not clearing anything, is it? All right, well, this is... Is it actually a clean environment? Let's see. What's going on with this thing? Oh, it's still starting. That's so weird, dude. All right, so we're gonna draw some signs, get different random signs with different phase and periods. Great. Now we're gonna pass in some y values. I guess we want to figure out. I don't know what's going on here. We're going to pass in some y values and what? So we'll draw the y values on the x values. Do inference. So we pass in x's and xy, the y values, some amount of computation. Create a choice map that maps model addresses y to observe values ysi. We leave slope and intercept unconstrained because we want them to be inferred. All right, so we get our observations. Yeah, what is this? So we create a choice map. So it's just like an empty choice map maybe, and then we go through the y values and assign them each y value to so it's like dynamically creating this dictionary-like object of this class choice map. And now we're going to use importance resampling. That's pretty nice and clean. I like that. So we do inference. Is there any kind of, so importance resampling is doing all the work, but we put that into a function. It returns one trace. So how does importance resampling work? Let me what do I want to say about it? I got some notes here on importance sampling. See if you can see this here. So these are my class notes, some lecture notes I use to teach on Bayesian inference. And importance resampling is an idea closely related to importance sampling and the envelope rejection method. One of the problems with using the rejection method is finding a good envelope and computing. So the envelope method is it's just a sampling method. And so this is supposed to help us do a little bit better. Importance resampling, like importance sampling, can in principle choose any proposal distribution with the same support as the target distribution. So it has the same, some distribution is generating the same variables. And there's no need to calculate any kind of bounding constant. It is therefore widely, so like with the envelope method, you need to figure out how to bound, you need some kind of bounding thing, which varies from problem to problem. It could be tough to come up with. So, but this method doesn't require that. But you need this, come up with a good proposal distribution. I imagine that this, Julia is going to, or Jen is going to do that for us. It's going to make that easy for us, perhaps like a uniform distribution or some kind of distribution, some kind of default proposal distribution that matches the distributions that we're trying to infer, at least in support. It's not exact, so the generated samples are only approximately from the target distribution, with approximation improving as the number of generated samples increases. Importance sampling was introduced earlier. We demonstrated an expectation of an arbitrary function g can be approximated using samples y from the probability distribution h. All right, so we propose from here, then we take our right, so we're just gonna we're trying to find the expectation of this function, and we can calculate these weights, which is the target distribution density divided by the density from the proposal distribution. and then we basically resample. So we sample from so great, we're going to sample a bunch of y values from our proposal distribution, compute weights, renormalize them, sample with replacement. This, of course, implies that you know the target, the target distribution, but for being Bayesian, I imagine that we can just work with the prior times the likelihood. And if we choose a proposal distribution, that also somehow, if you construct this such that the marginal distribution of the data cancels out. All right. So great, let's go back. What happened? All right, there we go. All right, so we're doing importance resampling. We do 100 samples, I suppose, and returns one trace. So it must just, I wonder how that works. I mean, because you would think that importance sampling would generate. Does it generate a bunch of samples and then it just picks one with a high weight? We could try it out if we could actually get this to work. Let's try it. All right. It's going to take forever. All right, so great. Then we get a trace. We draw a picture of it. Then we do some kind of list comprehension, get a bunch of likely traces, and just get samples from our sphere. That's really nice. Actually, I'm actually liking this a lot. This is. You know, I've played with a few of these probabilistic programming languages now, and this one feels pretty smooth. I'm curious to see what happens when we get to predict some new data. Let's see what happens. Do we use? Oh, we take a trace. So you're taking. So I guess like for arguments from the posterior, you create a function that takes in a model and a trace. And you take the things that are happening in a trace, and then you generate from a model using the trace elements as constraints. Pretty good. And then generate the new y value. Values. The cell below defines a function that first performs inference on observed data and then runs predicting new data to generate predicted y coordinates. So now this will probably do this thing many times. So we do inference step once, get a trace, and then predict the new data, and then plug that into this list here. Great. I like this kind of you do inference in one step and then the operation on the, so rather than kind of getting a sample of, getting a bunch of samples from a posterior, first you just sample one thing from the posterior, and then whatever it is you plan to do with that posterior, you do to that sample, and then so that's posterior inference step happens in there's a pairing between, you don't do a bunch of samples first and then do a bunch of transformations of the samples afterwards. You get one sample and then transform it. I don't know why that's better, but I like it. Plot some stuff. Great. So that'll make posterior predictive checks a lot easier. So what are we doing now? And then I guess you can see here, it's pretty clear, like in this inference step. Where'd it go? Do inference. So yeah, you could, if you're writing an inference like this, you can see how you could you can chain up a whole bunch of inference algorithms. So you could take a trace, you can do something, get a trace, and then pass that trace into maybe another inference algorithm. And I'm also used to Bayesian approaches where you have to use some kind of some probabilistic programming languages where you have to use some kind of something like condition or something that says, take into account evidence. I guess here, so here's our evidence. And we're still kind of doing it by hand here by creating, so we're thinking of a execution as a bunch of random choices, and then so this is a bit verbose as opposed to, say, something that just says, condition this model on this on these observations, but nonetheless I like it. It's because you're working with, so you're not working, so once you observe data, once you have some evidence, the abstraction you're working with is not a model, but it's this map that maps random choices in the model to actual values, which I'm not sure how I feel like. I like the idea of just working with the model as a kind of core artifact of inference as opposed to some new thing, this choice map thing. And so we're using the model anyway, an importance sampling. So we have it'd be nice if this thing were just living inside of this thing. So if these two abstractions are separate, I'm hoping I see some advantage of that. But all in all, it's a very clean workflow. Yeah, this thing's not working. Calling other generative functions. So what else? What other good stuff do we have in here? We are looking now at infer and predict. We plot some stuff. Do some posterior predictive checks. Calling other generative functions. In addition to making random choices, generative functions can invoke other generative functions so we can nest things instead of other things. That's always nice. To illustrate this, we write a probabilistic model that combines the line model with the sign model. This model is able to explain data using either model, which is, of course, so it's like a mixture of models or model selection. So that's great. Right, you flip a coin between either model. That's fine. That's pretty... Unbounded number of parameters, non-parametric model, in other words. So it can do Bayesian non-parametrics. And what else can we do? Come on, show me something nice. That's it. All right, well, let's see. Scaling with combinators and the static modeling language. This tutorial shows how generative function combinators and the static modeling language are used to achieve asymptotic time scaling of inference algorithms. That's great. Particle filtering. All right, so we got some clever inference techniques. Bottom-up introduction. So maybe that's what we can look at next time. And then we got some MCMC and Gen. Okay, this is looking pretty mature and pretty... It's nice and clean syntax. I might use this to teach how probabilistic programs work. That's interesting. Gotta put that in a statement. Cool. Well, that's gen.jl. I plan to keep looking at some of these probabilistic programming languages and see what other interesting little items I can find inside of them. But thanks for watching, and hope to see you next time.